To continue our understanding of the stoichiometry, we're going to now apply a couple more steps to this so it's a little bit more detail oriented because from our prior unit, we know that we can't go into the lab and count out a number of moles, but what we can do is measure out a number of grams of a element or compound using a digital scale to determine how much we need to put in the reaction or how much we're going to get out of the reaction. So we're going to be factoring in some mass conversions, just like we did with our unit on moles, into this concept called stoichiometry. Okay, so really and truly, like I've been saying all along, the labels are really going to drive the number of steps and what you need to convert from or convert to. And then we're also going to be factoring in still this balanced chemical equation with all of the mass to mole conversions that we've been doing. Okay, so for this first example problem, it says how many grams of oxygen gas will be required if 2.5 moles of aluminum react to produce aluminum oxide. So first of all, if you notice, we've got an unbalanced chemical reaction because we're putting one aluminum in and getting two out. So we need to balance the system by putting the appropriate coefficients. And then what I'm going to also encourage you to do is mark underneath your reaction, what is it that we're solving for? So we're solving for X grams of O2. And then what is it that we're provided? We're provided 2.5 moles of Al. Okay, so again, we know that these numbers represent the ratio of the number of pieces. It doesn't factor in their weight. So it doesn't say 4 grams of aluminum and 3 grams of oxygen. What it's telling you is 4 moles of aluminum and 3 moles of oxygen will produce 2 moles of aluminum oxide. Okay, so if we're doing mole to mass stoichiometry, this is going to require two steps. We need to balance the reaction, and then we have to do mole to mole and then mole to mass. So we're going to be factoring in this equation that we've used before. 1 mole of any element or compound is equal to its molar mass on the periodic table. Okay? So if we start with 2.5 moles of aluminum, and now the element along with the label is part of your work because we're going to be chemically converting one element to another element. So eventually we want those labels to cancel out. And so this label here, moles Al, is going to go in the denominator. And the only thing that we can convert moles to is grams, but we don't want to go to grams of Al because eventually we want to switch over to this reactant. But we now know from our other video that we can use these coefficients as a mole to mole ratio. So we can convert moles of any element or compound within the reaction to another component of the reaction because we know that for every 4 moles of Al, we're going to require 3 moles of O2. Okay? So again, moles and Al will cancel out, and we've essentially just done a stoichiometric ratio conversion of how much oxygen we're going to need, but we want to know how many grams of oxygen we're going to need, so we're going to set up another conversion factor, and again, the goal is to cancel that label out and convert it to the only thing that we know we can now convert moles to. We can convert moles to grams, which is what we're trying to solve for. So we're going to put grams O2 in the numerator. And then looking at your periodic table, oxygen has an atomic mass of 16, but we have 2 of them. So for every 1 mole of O2, it's going to weigh 32.00 grams of O2. Again, this component, which we did last unit, comes from your periodic table. Okay, so we need to crunch a few numbers here. 2.5 times 3 divided by 4 times 32. We get a nice even 60 grams of O2, which is the label required because it's the only label that's left that hasn't canceled out. Okay. So the rest of the examples on this worksheet are similar in work to this one. Okay, except we got to watch what we're starting with and what we're ending with. So I'd encourage you at this point to kind of pause the video and try this out yourself, see if you understand the process, see if you can kind of signal through the work, and then we'll resume with the correct answers. All right, so you notice that we kept the reaction the same just for a little bit of simplicity. So our ratios are still 4, 3, and 2 for both examples. Except in example 2, we're now starting with 13 grams of aluminum, and we're solving for X moles. We're solving for X moles of product, X moles of aluminum oxide. And then in example 3, we're starting with grams and ending with grams. We've got 40 grams of aluminum, and we want to know how many grams of oxygen will be required. Okay? So again, we've got the necessary pieces. We've got the tools now to go from moles to moles, to go from moles to grams, and to go from grams to moles. It just depends on whatever our starting information is and what we're trying to convert to. So since we only have 13 grams of aluminum to start with, what we want to do is, in order to convert a reactant to a product, we have to use these coefficients, and these numbers up here, again, only represent a mole to mole ratio. So the first step, anytime we're given grams, is to figure out how many moles that's equivalent to. Okay? So again, going to the periodic table, anytime we're using a mass or ending with a mass, we need to look up and find that the mass of aluminum is 26.98 grams per mole of aluminum. So that we cancel out grams, and we're left with how many moles that would be equivalent to. So we're working with about a half a mole here. And then this is our only label that's left over. And again, the goal is to eventually convert Al to product, Al2O3. And so we know that once we've got moles of aluminum, we can convert to moles of product by using those mole to mole ratios. So for every 4 moles of Al, we're going to produce half as much, 2 moles of Al2O3. Okay? And again, moles Al will cancel out. Okay? So again, we got to crunch a few numbers. We're going to multiply by every numerator, divide by every denominator. So we could do 13 divided by the molar mass, 26.98, times 2 divided by 4, and we get 0.24 moles of aluminum oxide. Okay, so we had about a half a mole going in, and then we have about a half ratio because we produce half amount of product at the end. So we end up with about 0.24 or a quarter. Okay. So then for this last example, we're going to start with a mass and we're going to end with a mass. So if in the first example we wanted to end with a mass, we needed the mole to mass ratio. And in the second example, we started with a mass, so we needed the mass to mole ratio. Both examples, when we were converting from one chemical to another chemical in the reaction, always used the same mole to mole ratio. Okay, so that's kind of the cornerstone of stoichiometry, this mole to mole ratio. That won't really ever go away, right? But the thing that might change it up and make it a 2-step problem or a 3-step problem, again, is the labels that you're starting and ending with. So here we're starting with 40 grams of aluminum, and in order for us to eventually convert from one reactant to the other, we need to utilize this 4 to 3 ratio, but we need to get our units into moles to make that 4 mole to 3 mole ratio possible. So the first step, like always, is to put your first label in the bottom. And since we have grams, we want to know how many moles it's equivalent to. And we can use the periodic table for that, just like we did in the second example. So 26.98 grams of aluminum is equivalent to a mole. And then we can convert moles, Al in the bottom, to moles O2 in question, and utilize that same ratio. So now that we've got the mole to mole conversion, we know for every 4 moles of Al, we need 3 moles of O2. But again, we're trying to get to grams. So just like we did in the first example, we're going to utilize the labels that are left over, and we know that we're going to put moles O2 in the denominator to cancel them out, and it's going to tell us that 1 mole is equivalent to 32.00 grams of O2. Make that 2 a little bit better. Again, to cancel out moles of O2, and by forcing all of the labels to cancel out in such a way, it aligns the work so that we use the correct division, multiplication, division, and multiplication to get the right answer. Again, this is the dimensional analysis, the kind of label canceling approach that cuts out all of the proportions and things like that so that our work is all lined up in one equation, this times this times this times this, and we can punch it all into our calculator at one time. So 40 divided by 26.98 times 3 divided by 4 times 32.00, we get a final answer of 35.6 grams O2, because that's the only label that we have left, and that is your correct answer.